Okay, so here in this video, I will make the final video for homework 5, and this is a brief summary of what we have done earlier. So we calculated a lot of things, and these are what we have to work on, like the remainder. For wild test, we wanted to show that, so the wild test is based on this guy. So we have to find its asymptotic variance, okay? And then if you find it, then you can just apply the quadratic formula, and then it will converge to chi-square 1. And criterion-based test was based on this, but it's uncertain what kind of standardization you have to do here. But in the end, I'll show you that all the three things should be the same. So you have to match this guy to the other guys. Hausman test was based on slightly different form, and its variance will be slightly different, can be different from the wild test, but anyhow, the formula is the same. Hausman test statistic takes this form. So in either case, we have to find the asymptotic variance. That is the main idea. So I will show you how to do that. First, whenever you work on this theory, so here, like underlying objects are y, x, z, and epsilon. Okay, we have only 4 random variables in our model, but like very simple tip is x, and z and epsilon are like more primitive or more structural, more fundamental variables, and y is just an outcome generated from the other guys. X and z and epsilon are exogenous variables in that sense, but y is endogenous. Y is generated, and y depends on all the other variables. So I recommend you use only x, z, and epsilon, right? So replace y with it's like expression based on x, z, and epsilon. Okay. So then, for example, I'm going to do that in the first step. So we will replace place y with other exogenous variables. So this will simplify a lot of things in many cases in general. So if you do not have any idea where to start the algebra, so I recommend this. Okay, so for example, in our notation, so in our notation, we have x, y average of x times y, and I will rewrite, let's write it, Control Enter, to have another line. So I recommend writing it this way, and then xi squared beta 0 plus okay, oops, right? So I removed y and expressed y in terms of x, beta, and epsilon. Okay, so if you want, you may rewrite this as axx beta 0 as possible, and ax epsilon. Okay, so you can rewrite y using other parameters. Similarly, zy can be written as xz beta 0 plus hat z epsilon. Okay, so we are going to use these guys. Then first, let's think about this. Then think about, let's consider, then it it will it can be written as, say, um, ZW can be written as, excuse me, it's my bad. We have to write it here, and we have to use this here. Okay, and then rewrite the things. Interestingly, so x beta and xz zx, actually these two are the same thing, so they will cancel out, and beta 0 xx will cancel out this term. So it simplifies a lot, right? In the end, what remains is x epsilon minus um, z epsilon times xx divided by xz. Zx, xz, they're the same thing. Okay, so we have this form, and I will move z epsilon separately. Okay, then let me show you how I do it. I am going to think about this as this. I will rewrite this as, so you may think it as, let me, excuse me. So 1 times minus this guy is a vector times so we will rewrite our formula in this way. And what I'm going to show you here, my strategies, is to show this. The first thing will converge in probability to something, which is pretty easy. So simply I will write it this way. And the second thing will converge in distribution to normal distribution for, say, let's say, covariance matrix, say A, whatever. Okay, so second part converges to normal distribution. I am going to apply the central limit theorem for the terms that involves epsilon. But this term, xx over xz, will be converging to a constant true expectation. Okay, so and then by the Slutsky theorem, we can show that the total thing will converge in distribution to normal distribution with this, that times A times the same thing, like this. Okay, so for simplicity, I will rewrite this as a B. Then we are going to have B times A B prime. So this will be V, right? This is VW, okay? So I just rewrote remember, I rewrite this much into this, right? This, right? And then I will show that this will converge to this guy. And separately, A will come from here, B will come from here. Okay? And so then P is simple. It is by the weak law of large numbers. So 1 is 1P is uh, minus uh, had a xx, so this guy. It is obvious that this converges to xi squared over xizi, right? So this is the low large numbers and the continuous mapping theorem, because I combine two low large numbers. This converges to this, and this converges to this, and the ratio is continuous mapping, so we can conclude this. Thus, so P is the P part. Is the first element is 1, and second element is this guy. We know P. And for simplicity, I'm going to write this as AXX, AXZ. So I believe I have defined this notation in the homework. In, in the question, you will find, I believe you will find this notation. Okay. Meanwhile, so we are going to handle this by the central limit theorem. It is easy to see that, say, x epsilon, z epsilon minus expectation, the same thing, with A equals variance of this guy. Okay, this is the standard um, central limit theorem. By the way, one thing I should have mentioned was, if the null hypothesis is true, by the central limit theorem, we get this. We need to, excuse me, not this, not here, right? So if the null hypothesis is true, then we know both are 0. This is 0. And under the homoscedasticity assumption, we have A equals this 2 by 2 variance matrix is given like this. Okay, so I believe it should be straightforward. And using the same notation again, I will write it as like this. Okay, so A is this guy, B is this guy. You just need to combine them in this form. So then B times A times B prime will become, it's more complicated. So this times, excuse me, it's my bad, like transpose must be here. Because of this transposition must be placed on the first term. So it was my mistake. So this transpose and this times and the same thing again. B again. Okay. So you have to do this algebra. So let me pick what I got. Where is it? Even though I see the answer, it's not easy to see what is what. Oh, very complicated. Okay, the answer is sigma squared first, and then AXX times, somehow I write it like this, AXX AZZ over AXZ squared minus 1. So this is what I wrote here. And I simplified this even more by replacing this term as by rho, 1 over rho, right? So where rho is correlation coefficient between x and z, which is square root of xi zi divided by xi squared and z squared. Okay, so let me, so the, excuse me, it's not exactly right, because the radical must be taken only on the denominator, right? Remember, this is the definition. So this is actually variance of x. This is covariance between x and z, variance of z, variance of x. So in the denominator, you have to have standard deviations, and this is covariance. So if you square that and reverse, you get this term. So it will be convenient to have this guy, okay? Or you can just expand everything without simplifying the thing, so that is also possible, but it will imply something. And remember, the covariance between x and z, correlation between x and z is a very important parameter in IV estimation, and it comes up again in testing. Okay, anyhow, we got this. So going back to the general formula, we are going to apply all these things back here. Okay, so we have this, and V was calculated like this. So you have to invert. Then the inverse of V, say wald test V, is this, and something like this. Okay, you you can like simplify maybe this one even more, but not a big problem. Then plug this back into our formula. N times, here replacing the inverse with this guy. Okay, so I'm not certain how much you can simplify. Let me see. So, not easy. Anyhow, so you like this is, you may simplify, you may just use this in here and see what you will get. Okay, anyhow, the basic idea is this asymptotic theory. Okay, then let me try the same thing for Hausmann test. For the Hausmann test, we start from this and like back to the starting point. And as before, I am going to rewrite x, y, y using other notation, other objects, like x times y is like this, and denominator is the same, minus z times y divided by zx. Z times y will be replaced by this guy. Then again, beta 0 here, beta like AXX is cancelled by the denominator. So beta 0 here will be cancelled out by this beta 0 because the coefficient cancelled out again. So here you only have x epsilon divided by xx minus z epsilon divided by xz. Zx, xz, same thing. Okay. Then, as before, I am going to rewrite this using vector. So the idea is in the second vector, in the end, we are going to apply the central limit theorem on xz and z, x epsilon and z epsilon. And what you multiply to them is 1 over hat AXX minus 1 over hat A XZ, right? So of course transpose here. And as before, we are going to apply the central limit theorem here, and it converges to something else. And we will show that like this. This and this, the first vector, converges to C, say, so that square root of this guy will converge to normal distribution C transpose AC. And we know A was given here. A is calculated above. We already obtained A, and by the weak law of large number, easily, C is 1, simply 1 over AXX, and second element 1 over AXZ. Okay, so now you have to calculate. So therefore, the variance for Hausmann test is this transpose this times this calculate that. Really, really annoying algebra, but I look at the cheat sheet and AXX AZZ minus AXZ square divided by AXX AXZ square again. Right. I'm not sure if it's exactly right. I believe I'm not so certain. Should be right. I don't know. Maybe this square should be deleted. So, all right. I think this is the final. You have to put parentheses here. Sigma squared must be multiplied totally. And so this is only the H part that will be plugged in back to here, right? So will be plugged back here. So that is another huge algebra, right? In here, we are going to plug that in. Back here, AXX AXZ divided by sigma squared AXX AZZ minus AXZ squared, something like this. So you have to calculate that. So this is Hausman test, and this is Wild test, right? So we are like, it is a huge algebra, but fortunately, actually, good thing, it's not that hard. It's a simple algebra because first, the prime does not matter. The transposition does not matter because it is one dimension. So you may just rewrite this as, just erase this much, and instead take square, right? It's square. It might complicate the problem a little more. Similarly, here, you do not need to keep the vectors because everything is scalar. So it's actually simpler. So you can simply square that. And you can delete the second thing. So then, yeah, still not easy. And then what is interesting is if you expand everything, the result here must be the same as the result from the wall test. Same thing here. This will be the same as this in the end. And then what you can compare here is you have to multiply something to this, the criterion based J test, so that all the test statistics are the same, right? So let me check it again if they are the same thing. Oh yeah. Oh, it's given. Yeah, in the question, I already gave you the answer. The answer is if you expand the algebra, if you expand this algebra, you are going to get, say, n divided by sigma squared. Numerator has AXZ times hat AXY minus hat AXX hat AZY squared divided by hat AXX hat AXX times hat AZZ minus hat AXZ squared. Okay, this is the result, right? You get this, and by the way, a few more comments. Even though I keep sigma everywhere, you do not know sigma. So in practice, you have to estimate the variance like by sigma hat, right? Like using the residuals, you have to calculate sigma hat, which is straightforward, so I do not talk much about that. And this will be the same thing here, okay? And now compare this to the J-test. So the criterion based test statistic should be the same. So but we get this. How different is this from the thing? I'm not sure. So you have to, so you have to multiply something appropriate, something. What do you multiply? I'm not certain. So you have to multiply maybe n over sigma squared to this one. Then it will be maybe the same as what you get here. Okay, so you have to standardize the criterion function by multiplying n over sigma squared. Then all three test statistics will be the same. Okay, so it was a very boring, tedious, long algebra. But as I said earlier, this is the simplest possible example, only with one instrument, one regressor. So, and yeah, this is how you find asymptotic variance and how you develop test statistics. Okay, thank you for watching. See you later. Bye.